Now over here, we have this horizontal rod of mass m and length L, which is supported by two strings which are making angle 37 degree, 37 degree. Obviously, they'll make the same angle. And now, out of these two strings, one string is cut. We are asked, what is the tension in the string? As soon as this string is cut, we have to find the tension in this. So, we have to find the tension in this string as soon as this string is cut. So, T is going to be in this direction. So, let's first of all write the equation for linear mechanics. So, T is in this direction, 37 degree is over here. So, this and this, suppose this 37, these two lines, they are parallel transverse. So, this is 37 degree. 37 degree and 53 degree, they are so widely used angles when we do numericals in physics. So, it is 3, 4, 5 triangle, and cos 30 is base by hypotenuse, that is 4 by 5, sin 37 is 3 by 5. We can use the values over here. So, when T is over here, this T has two components. Let's break it along x and y axis. So, T cos 37 and vertical component comes out to be T sin 37 degree. Mg is acting over here. This Mg is acting over here. So, what we say is, that is along x-axis, if we say, that is net force along x-axis is equal to mass into acceleration along x-axis of what? Acceleration of center of mass only. So, this means T cos 37 degree is equal to m into ax. What is T into cos 37? Cos 37 is 4 by 5. M goes over here. So, 4T by 5m is equal to ax. Similarly, once ax is found, similarly on the same lines, for along the y-axis also we can write the equation. Eventually, this center of mass will be falling down. So, we can write that is mg minus T sin 37 degree is equal to m into ay. We can just put the values and we'll get some ay also in terms of T only. So, we have got ax, we have got, and we have got ay also. So, we have got ax and ay. Ax will be in this direction, ay will be in this direction. So, we have got ax and ay in terms of T. So far, we have got this. Now, we can take the torque about this axis, about the center of mass. Torque of mg will be 0 about this. Torque of T cos 37, that will also be 0 about this, because line of force is passing through the axis of rotation itself. So, the only torque will be because of this, that is torque of T sin 30. If we intend to apply torque about C, we use I into alpha, that is I will also be about this axis. So, it is T sin 37 degree force into perpendicular distance between line of force and acceleration. So, this is going to be L by 2. If the total length is L, so it is going to be L by 2 is equal to I is going to be ml square by about this is 12 into alpha, right? If we get alpha, so obviously this point, so this is going to rotate like this, this will rotate like this. Because of this, the tangential acceleration of this is going to be equal to r alpha. So, that is going to be, r is going to be L by 2 into alpha, right? So, there is going to be tangential acceleration of this, which is L by 2 alpha. Alpha is, we can put it from here, that will also in terms of T only. Now, if we look at this end, so this end B, if we talk about, this is the net acceleration is going to be vector sum of these three accelerations, that is ax, ay, and this at is equal to r alpha. Ax is over here in terms of T, ay is here in terms of T, and this is, and this at is equal to, that is r alpha is also in terms of this. And this is a string. This is a string. If we draw over here, then we say that is the string is in this direction. The string is in this direction and it is supported over here. This is in D and this is in B. This is B over here. And this angle is 37 degrees. Now, point to be noted is that with this is falling, at this instant, this string will remain taut. This string will remain, the length will not change, it will remain taut. So, it is almost acting like a rod. So, it means the distance between this and this point, between B and D, that will remain same. That means the relative velocity or relative acceleration of these 2 points B and D, that should be equal to 0. This is already stationary, there is no acceleration of this. Similarly, the acceleration of this along this line, that should be equal to 0. So it means the component of all the accelerations along this line, that should come out to be equal to 0. So if we look at the components of all these accelerations along this line, so AX will have a component. If we draw this line, so this is AX over here, this is AY over here, this is AX over here, AT over here, AY over here. So when we say that net acceleration along this line should be equal to 0, so the component of this acceleration along this way is going to be AX cos 37. AX cos 37. So if this is 37, so this is 53 degrees. So component of this acceleration this way is going to be AT cos 53 degrees. So this job is also done. So now is this. So now is only AY is left. We have to find the component of this acceleration AY along this line. So obviously that will be in this direction. Component of this acceleration along this line will be in this direction. So this is 37 degrees. So this is also 37 degree, vectorially, vertically opposite angles. So if this is 37, this is 53 degrees. So AY component this way is going to be AY cos 53 degrees. So this also goes off. So these are acceleration components along this line, and net acceleration of B along this line is equal to 0. It means AX cos 37 degree plus AT cos 53 degree should be equal to AY cos 53 degrees. In this equation, you can just put the values of AX, AY and etc. and you can find the value of T, and T will eventually come out to be 15 mg by 52. You have to just put the values and you can get the answer. I would advise you that as you do this question once again on your own, so that you are thorough, that is how the accelerations, they are kind of a superimposed, vectorally superimposed. So if we review, that is what we have done. First is we have broken this 2t. So first we have broken this t into its components. One is along the x-axis, the other is along the y-axis. Along the x-axis, that's why because of this, the acceleration center of mass will be along the x-axis. We have used Fx is equal to m into Ax. So we have got the value of acceleration along x-axis in terms of t. Similarly, along y-axis, if we see, we have one force, that one is component of tension in this direction, the other is mg in this direction. This will fall down with some acceleration, so mg is greater than t. So mg minus ty is equal to m into acceleration along the y-axis. That will also be in the downward direction. So we get Ax and Ay in this direction. Ax and Ay, we find the Ax and Ay, we have got it in terms of t. Now because this is also rotating, this will also be rotating about like this. So this point is also going to have some acceleration, that is A tangential, because of alpha, that is A tangential is equal to R alpha. We are going to have this angular acceleration also, and because this alpha, we are going to have this tangential acceleration. This point is going to have A tangential also. So the net acceleration of this point is going to superposition of all these three accelerations vectorially. One is A tangential, the other is Ax, the other is Ay. So then what we do is, that is, we say that is the length of this string is constant. There is no relative acceleration between this point and this point. The acceleration of this point, which is fixed over here to this support, is equal to 0. So that's why the net acceleration of this along this line, that should also be equal to 0. So the component of this acceleration along this, component of this acceleration along this should be equal to component of this acceleration along this. So these components should be equal to this. So then there will not be any acceleration along this string. When we write the equation from there, eventually we get the value of t, which comes out to 15 mg by 52. You can check it yourself.